Okay, here is part 3 of our Lewis structures practice. So, we have some situations here where we have multiple bonds, and what I've done is just written out the symbols for the atoms first. So this is a little confusing. C2H4, so we have 2 carbons and 4 hydrogens. And in general, the one that has more is going to be the one that surrounds the central atom. So, for example, over here, carbon and 2 oxygens, the carbon will be the central atom, and the oxygens will surround it. Similarly, here, carbon will be the central atom, and the hydrogen and nitrogen will surround it. So I just wrote out the basic structure, and what we're going to do is, as I've started here, fill in valence electrons to come up with the Lewis structure. So, with the oxygen, we know that oxygen has 6 valence electrons, and so adding them up gives a total of 12. This is the little E symbol with the negative sign to indicate electrons. And normally we would start out, let me get this part erased here. Normally we would start out doing something like, okay, pen, here we go. Normally we'd start out with, let's see, we have 1, 2, 3, 4, and then we might assume 5 and then 6. Okay, so start out by assuming that each atom will share 1 electron. So we'd have 1 here for this oxygen, 2, 3, 4, 5, 6. And we would assume that, okay, so here's a bond. But then you're going to look at each atom and see how many electrons the atom feels like it has. So this oxygen has 1, 2, 3, 4, 5, 6, 7. Similarly, this oxygen feels like 1, 2, 3, 4, 5, 6, 7, which is close to the full octet, meaning 8 valence electrons, but not quite. So the oxygens will be like, hey, what if we shared another electron? So this oxygen would share 2, and then have 1, 2, 3, 4, 2 lone pairs. And then this oxygen would share 2 electrons and have 1, 2, 3, 4, 2 lone pairs of electrons. They have a bond and a bond. Therefore, each atom feels like it has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it, which is what it wants. So the actual structure we would draw is something like this. We have an oxygen atom, 2 bonds, and each of the oxygen atoms has 2 lone pairs of electrons, like so. And just to look back at our 12 full electrons, and so 6 pairs, 1, 2, 3, 4, 5, 6. Okay, looks like it works. Over here, C2H4. Alright, each carbon has 4, and each hydrogen has 1. So adding them up gives us a total of 12 electrons. So we're looking for 12 electrons, looking for 6 pairs. And this I'm going to start with carbons. Carbon has 4. So if we assumed 1 and 2 and 3, okay, so that's 1 electron for each. it's going to have this stray electron out here. And for this other carbon, we're going to assume 1 sharing with the other carbon, sharing with the hydrogen, sharing with the hydrogen. And each of the hydrogens, of course, so hydrogen contributes 1, hydrogen contributes 1, hydrogen contributes 1, and hydrogen contributes 1. So we have, this is all good. We have a bond, we have a bond, we have a bond, we have a bond. And the hydrogens are happy, but let's take a look at these carbons. Oh, I'm sorry. This carbon here has its 4th electron just hanging out. So carbon has 1, 2, 3, 4, 5, 6, 7. Alright, so it looks like it's close, but similarly to the oxygens, they shared 1 electron each between them, and they feel like they have 7, so it's pretty obvious that they meaning these 2 carbons, are going to share these extra electrons and bring them in here. So if this carbon has shared, if this carbon has taken this electron and shared it, and if this carbon has taken this electron and shared it, we now have a double bond between the 2 carbons, and each of the carbons feels like they have 2, 4, 6, and 8 valence electrons and are happy. So the actual structure has a carbon-carbon double bond with single bonds to the hydrogens, and all of the electron pairs are taken up as bonds. We should have 6 electron pairs, 1, 2, 3, 4, 5, 6. So again, the electron pairs can either be bonds like these, or can be lone pairs that just hang out away from the bonds. Alright, CO2, carbon dioxide. Start with the carbon, and again we're going to assume 1 each for the oxygens, and then have a lone pair. For the oxygens, we know we have 6, so 1, 2, 3, 4, sharing 5, and then 6. And over here, 1, 2, 3, 4, sharing, and 6. And so let's count them up. Let's see. Carbon has 1, 2, 3, 4, 5, 6. Not so good. Oxygens have 1, 2, 3, 4, 5, 6, 7. So none of those 3 atoms has a full octet. We're going to have to do more sharing. So if we were to bring this in to form a bond with this electron, and this electron to form a bond with this electron, we would end up with carbon sharing 2 each with the oxygens, and each oxygen sharing 2, and then having 2 lone pairs, so sharing 2, having 2 lone pairs. We have a double bond between each of the carbon and oxygens. And the oxygen feels like 1, 2, 3, 4, 5, 6, 7, 8. And similarly, 1, 2, 3, 4, 5, 6, 7, 8. So the structure would then look like double bond between carbon and oxygen, double bond between carbon and oxygen, 2 lone pairs off each oxygen, and voila. Alright, number 5 is the same as number 2, so we don't have to redo that. Number 4, HCN, carbon, oh wait, I already have it drawn, never mind. Let's try, assume carbon will share 1, and share one, and then have a lone pair. So always first assume that the atom will just share one to form a single bond. Hydrogen will, of course, just share one, that's all it has. And nitrogen, oops, I forgot to write out my total number of electrons. So 10 total electrons. We are assuming 5 pairs. Nitrogen has 5, so 1, 2, 3, 4, 5. That looks like it works well. Let's count them up. Hydrogen's happy. It has 2. Carbon has 6. Not so happy. And nitrogen has 6. All right, so we're getting closer. If we were to bring in these 2 electrons to form a double bond, carbon would feel like it has 1, 2, 3, 4, 5, 6, and 7. And same with nitrogen, 1, 2, 3, 4, 5, 6, and 7. So it's not going to work, but we're getting closer. Let's bring this in and bring this in. So we have 2 shared between the hydrogen and carbon, yet 3 pairs, 1, 2, 3, 4, 5, 6, shared between the carbon and nitrogen, and then this lone pair is the only one left on the nitrogen. Do we have 10 total electrons, meaning 5 pairs? 1 pair, 2, 3, 4, 5 pairs. And carbon has 1, 2, 3, 4, 5, 6, 7, 8 around it. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 around it, and they are happy. The structure then looks like single bond between hydrogen and carbon, triple bond between carbon and nitrogen, and 1 lone pair on the nitrogen sitting off to the side. All right, last one. Nitrogen gas, so 5 valence electrons. Nitrogen is 5, giving a total of 10 electrons. So we expect to see 5 pairs. 1, 2, 3, 4, and 5. Again, this is how we start all the time. Assuming a single bond, looking at the number of valence electrons that the nitrogen atoms feel like they have. We have 6 for this guy and 6 for this guy, not enough. So we could bring in 1, and then each would feel like 1, 2, 3, 4, 5, 6, and 7. Not going to be enough. So we're going to bring in an additional pair, forming a triple bond. So we have 1, 2, 3, 4, 5, 6. Don't forget about these guys. Each nitrogen has a lone pair of electrons. So this is a triple bond. Each nitrogen feels like it has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it, giving us therefore a triple bond and a lone pair on each. Okay, so this is what nitrogen gas looks like. It's part of our atmosphere.